Hello guys, today we will talk about polynomials. Probably you have all seen polynomials. Polynomials are expressions like this. Say, here is a polynomial of degree 3 with variable x. So first, let's talk a little bit about intuition related to polynomials, and then I will give a formal definition which looks very much like the definition of complex numbers. So, intuition. So notice a polynomial has coefficients. These are these numbers which we put before a variable x, and in general, we can take, instead of integer numbers like here, arbitrary field, because you see here we have addition, multiplication. It makes sense to do it over any field. So we start with any field. Let f be a field. So this is a field which is usually called the field of coefficients of a polynomial. And then a polynomial is an expression like p of x equal to a0 plus a1x plus ... plus an xn, or something like this, where this elements a0 up to an are some elements of the field. Perfect. What we can do with such objects? So one can add and multiply polynomials. So here is an example. For instance, if we have a polynomial something like 1 plus x times 1 minus x, it equals to 1 minus x squared. And we use the usual rule of multiplication and operating with a variable. Okay, what else can we do? So this is one thing we can do. Another thing we can do is we can plug in an element of f. So if x0 is an element in f, we can define p of x0 to be the following sum. So we just write x0 instead of x. And we get in this way an element in a field. So remember, if a0 was in some field, a1, x0, and so on, you can add and multiply elements in a field, so you get again an element in a field. So in this way, we can view a polynomial as a function from a field to itself. And probably this is exactly what you have been doing. So you were looking at polynomials where variables are real numbers, and then you think of it as a function. You plug in something and you get something, and you can draw a graph or whatever. Okay, so third thing which we do with polynomials, we can, for instance, differentiate. And for that, we take a polynomial p of x, and we define its derivative to be another polynomial, which is a1 plus a2x times 2 plus 3a3 x squared plus and so on. And notice that this totally makes sense over arbitrary field. So in any field you can define what 2 times a2 means. 2a2 is just, a2 plus a2, and so on for other coefficients. And so this makes sense in arbitrary field, and you don't need to think of it as a function. You don't need to take limits. You can just say this is the definition. And usual properties will hold. For instance, if you take a pair of polynomials and multiply them and take the derivative according to this rule, you will get the usual formula. Okay, finally, what else can we do? That's it. Also notice polynomials form a commutative ring. So polynomials form a commutative ring. In the usual sense, we defined what a ring is last time, and so what it means that we have a set of polynomials, we can add them, multiply them, all the usual rules hold. Commutativity of addition, associativity of addition, there exists zero polynomial which is just zero, there exists one polynomial which is just one, without any variables going on, and all axioms hold, and you cannot divide polynomials. You don't get a polynomial in this way, and this is the reason why it's not a field, but all other axioms of a field hold. So we call such thing a commutative ring, and it has a name, so named f and x in brackets. So this is a usual notation for polynomials. For instance, r and x in brackets are usual polynomials with real coefficients. With real coefficients. So this is the object we are very used to. Let's start with a formal definition of a polynomial now. So formal definition. Okay, so this definition mimics our definition of complex numbers. So remember, complex number is a number a plus bi, and we just said that by definition a complex number is a pair of real numbers. So similarly, a polynomial will be a sequence of elements in the field which are basically just coefficients of the polynomial. So let f be a field, a polynomial P is a sequence A0, A1, A2, and so on, where AI are inside F, and all but finite number of AIs equal to 0. Okay, so of course mnemonics is that the sequence A0, A1, and so on will eventually be the same as a polynomial A0 plus A1x plus and so on. Perfect. So next question is how to define addition and multiplication. So for this, let's just remember how we do it for usual polynomials. So if I have a polynomial p, which is a0 plus a1x plus and so on plus anxn, and q, which is equal to b0 plus and so on plus bm xm, then p plus q, we just sum up the corresponding coefficients. It's a0 plus b0 plus a1 plus b1x plus and so on. And for pq we do something much more funny. So the degree 0 term will be a0 b0, then a1 b0 plus a0 b1x plus and so on. And the general rule is that if p0 equals to c0 plus c1x plus c2x squared plus and so on, then cn equals to sum ai bn minus I from I equal to 0 to n. So this is a definition of a product of polynomials, but if we treat them as sequences, we can just uses formulas to define addition and multiplication. So now actually define addition and multiplication as follows. So let P be equal to a sequence A0, A1, and so on, and Q equal to a sequence B0, B1, and so on. Then P plus Q is just a sequence A0 plus B0, A1 plus B1, and so on. And P times Q is a sequence C0, C1, and so on, where Cn equals sum ai, b, n minus I from I equals 0 to n. Okay, so we have defined addition and multiplication. Notice that if all but finite number of ai's is equal to 0, and similarly for b's, then if we add up the corresponding sums, also all but finite number of the sums will equal to 0, and similarly with this coefficient c's. It's a little exercise, but it is really easy to check. And then a proposition is that so the set of polynomials with coefficients in f is denoted by f of x. And then proposition is that f of x is a commutative ring. So let's think a little bit about that. So a commutative ring is a set, and there should be two operations, addition and multiplication. So the set is a set of sequences, and this is how we add and multiply them. And they should satisfy lots of properties, and almost all of these properties are obvious. So addition is associative. That's true for every coefficient basically here. Addition has a 0, and of course 0 is just a polynomial which is a sequence 0, 0, and so on. And 1 is a sequence, is a polynomial 1, 0, 0, and so on. And then checking all properties of addition and multiplication is really easy, except maybe associativity of multiplication requires longer formal proof, but probably everyone can do it. Notice that it is a commutative ring, so which means that all axioms of a field hold except one, the last one. You cannot divide polynomials. So you cannot find, if you have a polynomial 1 plus x, you cannot multiply it on something to get 1. That never happens. So for instance, this one is not invertible, and so it's not a field, it's actually a commutative ring. Wonderful. Now let's relate this formal definition with usual form. So how the sequences are related with this form of writing what a polynomial is. So first, let's introduce the following notation. So notation is that polynomial 0, 1, 0, 0, and so on is denoted by x. So it is just a notation for this polynomial, and then one can easily check that x squared is equal to, so the first coefficient is just according to this formula with Cn being sum ai bn minus I n equals 0 to n. The first is just 0 times 0, the second is 0, 1 plus 1 times 0, the third one is 0 times 0 plus 0 times 0 times 1 plus 1, and then 0 and so on. And similarly, xn is just 0, 0, 1. So this is at position n plus 1, and then 0, 0, and so on. So this is just taking powers of this particular polynomial, and it looks just this x power n variable. And then a polynomial a, 0, 0, and so on, which is denoted by a. So notice that in this way the field f just sits inside the ring of polynomials fx. And if you think about it, when you add and multiply such sequences, you do it exactly as you add and multiply numbers. So actually, operation of addition and multiplication here agrees with f of x. So you can think of these polynomials as just elements of f. And then, of course, using the definition of addition, it's really easy to see that a polynomial a0, a1, and so on just equals to a0 plus a1x plus anxn, and so on. And this expression is finite because almost all but finite number of ai's vanish. Perfect. So, and then we can formally define everything I talked about in the introduction to this polynomial topic. For instance, so definition. So if x0 is an element of the field and p is a polynomial inside f of x where this p equals to a0 plus a1x plus and so on plus anxn, then p of x0 is by definition just sum a0 plus a1x0 plus and so on plus an x0 power n, and this is just an element of the field. So again, you can think of it as a number. And so a polynomial is a function from f into f, sending element x0 inside f to element p of x0 inside f. Fine. So this is how we define plugging in a number inside a polynomial. The next very important definition is a degree. So let p be a polynomial inside f of x, and then degree of p is the minimal number such that ai is not equal to 0. So I think of p as this one. So basically, this degree is an integer, which is the integer where the coefficient is not equal to 0, and this is the biggest one of those. So for instance, degree of a polynomial x cubed plus 3 is equal to 3, or degree of polynomial 1 minus x is 1. And also it's convenient to make a little notation. So you can think of degree of 0. So it's a question what degree of 0 actually should be, but usually it is convenient to say it is minus infinity. So basically a number less than any other number. And then all the properties will be true. Properties of degree will be true. So what are these properties? So little fact is that degree of a product p times q is equal to sum of the degrees. And this is simply because when you multiply two polynomials, then basically you add up the degrees between each terms, and if you want to find a maximal degree in the product, you just multiply monomial of maximal degree in P with monomial of maximal degree in Q, and you add up their powers. And also degree of a sum. So usually it will be equal to maximal of 2 degrees. But what might happen is that their terms of maximal degree might cancel with each other, and then you get a smaller degree. So eventually it's just less or equal than maximum of degree P and degree Q. Okay, here is an example. For instance, P equals 1 minus x and Q equal 1 plus x. And then degree of P plus Q is 0, which is less or equal than maximum of 1 and 1. Notice that if you put one of the polynomials equal to 0, this still holds if you think of minus infinity as such a number that if you add it up with anything, you will get still minus infinity.